Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
We now arrive at really where you want to be with infinite geometric series, which is applications. It is assumed that you have watched my videos on geometric series and geometric sequences and infinite series and partial sums of geometric series up to this point. So hopefully you have, because otherwise this whole entire video will be like Greek to you. Unless you're Greek, then it'll be like Japanese to you. Unless you're Greek and Japanese, which it'll probably be just totally fine, I suppose. All right, so applications of infinite geometric series. Every single one of these is just different. I mean, there's no real way to summarize how to deal with an application of a geometric series in one particular statement. So I'm just gonna I picked three representative examples. Actually, really, nothing's representative, but I just picked three examples to showcase kind of how you would approach these problems. But there's going to be a lot of pattern recognition in each of these. So the very first one, a particular ball rebounds to half its height from which it is dropped. Use an infinite geometric series to approximate the total distance the ball travels after being dropped from 1 meter above the ground until it comes to rest. And we're assuming that it probably will never come to rest, to be very honest with you. The visual is like this. It's dropped from 1 meter, boom, and it goes up to half its original height. Boom, and it goes up to half that height. Boom, and it goes up to half that height, and so on and so forth. And it does that forever. And we're being asked to find the sum of all these distances. Like the first distance that it fell is 1. Then it rose a half. But then it falls a half. And then it rises, right? But you don't want to say rising a half and falling a half cancel. You don't want to do that. You want to add those two up. So we're going to have to be somewhat creative with this. I'm going to go ahead and write out the summation. So it fell 1, and then it climbed a half, and then it fell a half. But again, I don't want to subtract that because we're adding that distance. We're covering all the distances that it did. And then the next group, it rises half of a half or a quarter. And maybe I should do a half squared. A half of a half is a half squared. And then it falls a half of a half. And then the next group, maybe I should do this in a different color. There we go. And I actually changed the half squareds because I wanted to introduce that notation a little bit later. And this goes on forever, by the way. So I'm just going to say plus ... What you really have here is a sum of 2 series. So I'm going to split it into 2 different series just so you could see it. You don't actually have to do it this way, I suppose. I suppose you could combine them up. Maybe I should do that. Yeah, I think I will. So you have 1 plus you have 2 of these halves plus 2 of these fourths plus 2 of these eighths. And you can kind of see the pattern, right? So plus, plus, plus. I don't want to change colors. I'll just say ... Now the one that's sitting on the outside, I'll leave that alone. The black ink on the left there, I'll leave alone. But I want to make sure that you truly understand what's happening here. We have a ball, it drops a whole meter. And then once it hits the ground, it rises a half a meter because it only rebounds to half its original height. And then it has to fall again half a meter, to get back to the ground. So the distance it covers in that red ink area is actually a half plus a half. Okay, and so on and so forth down the line. I just want to make sure that everybody is kind of on board with this idea. And we want to know the total sum of all of those bounces. Like, what's the total distance if I went on forever and ever and ever? Well, just like we did in the previous video, we'll look for a pattern for a geometric sequence first. So ignore the 1. I'm going to off to the right hand side here. I'm just going to list out our values of what looks to be our series or sequence. It's 2 times 1/2, and then 2 times 1/4, which is 1/2 squared, and then 2 times 1/2 cubed. Okay. And so on and so forth down the line. And you could see that the initial value, at least for the colorful chunk right here, is 2 times 1/2, which we know is 1. I know, I totally get that. And each step of the way, we're multiplying by a half. If you multiply half by half, it becomes 1/2 squared. In the next step, you multiply by another half and you get to a 1/2 cubed. I suppose I didn't have to write the squares and the cubes. I could have left it as 1/4 and 1/8. But at least this tells me that's my common ratio. And again, like I did in the last video, I'm going to make a little note here that the absolute value of that common ratio, which is the absolute value of 1/2, is less than 1. That's critical because then we know that we can use this formula right here, the summation n equals 1 to infinity of a times r to the n minus 1. That will become, if r is less than 1 in magnitude, a over 1 minus r. We've proven that, well, sort of. You need calculus to prove it, but we did our best. And so I would like to use that. Now remember, this sequence that I'm creating right here does not include the number 1, that initial black ink off to the left-hand side. And that's totally okay. I could add that later on. So this sequence I'm going to write over here, it's a sub n is equal to the very first value, which by the way is 1, 2 times 1/2. Okay. And then the common ratio to the n minus 1. Well, that's actually a super nice sequence. Very, very nice sequence to deal with. So let's go ahead and insert that here for the colorful stuff. So this is equal to a summation n equals 1 to infinity of a, which we said is 1, times r to the n minus 1. You can double check that. When n is equal to 1, you will get 1/2 to the 0th, which is 1, which is exactly what this is. When n equals 2, you get 1/2 to the 2 minus 1, which is 1/2, which is the same thing as 2 over 4, so that works. And so on and so forth. Down the line, you could test it out if you want. But we happen to know that this summation can be traded out because, again, the common ratio is less than 1 in magnitude. We could trade that out for a, which is 1 in this case, over 1 minus r. And that would be 1 plus multiplying top and bottom of that by 2. We get that. And is that right? 2, yep. And that's 2 over 1. So this is 1 plus 2 or 3. So it has traveled, if it's allowed to bounce forever and ever and ever and eventually settle down, it travels 3 meters over that entire distance. That's pretty good, right? Yeah, I think that works beautifully. So this is a good example of an application of geometric series that they just go on forever. You just keep adding values. Notice how I kind of set this up. I started with just a picture. Really does help out, I promise. And then I started kind of looking for patterns within that picture. Oh, half plus half, 1/4 plus 1/4. I color coded, makes it a little bit easier. Then I grouped things up kind of nicely. I have 2 of those red inks, 2 of those green inks, 2 of the blue inks. And then I just went ahead and created a sequence off to the side based upon that stuff, not the number 1. The 1 out front didn't exhibit a pattern to me, so I left that out for computation after everything was said and done. That's kind of what you're looking for. Patterns like that. All right, let's try another one. So I decided to remove an example here. That's why that's crossed out, because the example I had created is actually a little more challenging for a pre-calculus course than I meant it to be. And some people might think that this one is as well, but I really think theoretically this is a pretty awesome example. So, but it's incredibly theoretical. So let's start talking about it. The Cantor set is constructed. Cantor was a mathematician back in the day. So a Cantor set was constructed by removing the open interval 1/3 to 2/3 from the closed interval 0 to 1. Now I'm going to help by visualizing this. Or I'm going to help you visualize this. So we have some closed interval from 0 to 1. And actually, to be honest with you, I tried to make this like really cool and erase things and stuff like that, but it was just too difficult. So I'm just going to go ahead and try my best to target this. So I'm going to remove the open interval from 1/3, which is probably around here, to 2/3, which is probably around there. So I'm going to call this 1/3 and this 2/3. And I hope you don't mind, but I'm going to go ahead and try to remove that. There we go. I actually successfully did that. So I've removed the open interval, which means that we have a closed interval from 0 to 1/3, and then a closed interval from 2/3 to 1. And then what we're going to do is remove the middle third of the remaining pieces. So I'm going to go to this guy right here, and I'm going to remove the middle third of this piece. Now, if you think about 1/3 of 1/3, well, that's 1/9. So I want to remove everything from 1/9, and maybe I'll write it this way. Well, I will write as 1/9 first, all the way to 2/9. I'm going to remove that interval right there. So I've successfully done that, and I'll say we have this closed interval left here. We're going to do the same thing on the other interval. We'll remove its middle third. Remember, the middle thirds are basically step sizes of 1/9. So 2/3 is the same thing as, what is it? Multiply top and bottom by 3, 6/9. So we're going to remove 7/9 to 8/9. That's the interval we're going to remove there. And again, it's a closed interval. All right. Now let's see. What else are we going to do? Zooming out. Let's see. Remove. Oh, all right. So then we're going to continue to do this, right? We're going to continue to remove middle thirds. So let me just do one last set here. And this time I'll just pause the video and do a bunch at once. All right. There we have it. I've just removed another set of middle thirds. If we continue this on, and I'm not going to do that because it really does get very long-winded, but if we continue removing these middle thirds forever and ever and ever, so I just continue, I cut out a middle third of this, a middle third of that, middle third, scroll over, middle third, middle third, middle third, middle third, and then whatever I have left, I do the same thing over and over and over and over again. I want to drive home the point that you will have a lot of points in space here because we're keeping all these endpoints. So I have 0, I have 1/27, 2/27, 1/9, 2/9, 7/9, 7/27, and so on and so forth. I have a lot of these numbers all over the place. And it'll be an interval that has a lot of numbers. But let's figure out what length we've actually removed from this. So what have we removed? Well, initially, we removed the center third. So let me write this down. There we go. We have removed the center third. And then after we removed the center third, then we went over to at that time it looked like this, okay? And actually, let me say it looked like this. Okay, it looked like this. And what we did is from that third, we removed a third, and then we had another one on the other side, which we removed a third from. So we removed 2 sets of thirds of thirds. Again, let me just say that again. This length right here is a third of the full length that we originally had. We originally had this length of 1. That is a third right there. And from that third, we cut out a third. There we go. So, but we did that as well on the other side. So we cut out a third of a third, or a third squared, from both of those sides. Now we're at a point where we have this length right here, and that length is a third of a third of a third. And we have 4 of those lengths, and we cut out a middle third. So we cut out from 4 things a third of a third of a third. Now I'm going to zoom in just to showcase that. This is a third of a third that we're looking at, this full length here. And what I'm going to do is just make it kind of very visual for you. This full length right here is a third of a third. Because again, we had this full length up top, which looked like this, full length, and we cut it down to a third. And that length you're looking at is a third of that third. And we're about to cut out a third of that third. Boop, just like that. So I have a third of a third of a third that I've cut out. And I do that for 1, 2, 3, 4 intervals. And then that leaves me with, give it a moment, 1, 2, 3, 4, 5, 6, 7, 8 regions. And from those 8 regions, I'm going to cut out a third of them. But each of those regions is a third of a third of a third, and I'm going to cut a third out of them. And I hope, without me having to say anything else, you see the pattern. This is what we're removing, and we'll do that forever. Remember, we always keep the edge points. We'll always keep the edge points, and there'll be more that we keep as we move along. We'll keep all the edge points from all the thirds that we cut out. So how much have we removed? How much is removed? Well, let's make a sequence out of this. We started with 1/3, and then we went to twice 1/3 squared. Then we went to 4 times 1/3 cubed. Then we went to 8 times 1/3 to the 4th. Well, if this is geometric, then we can call that A. And the question is, what did I multiply by to get to the next point, or the next term? Well, I definitely multiplied by 2 because you can see it right here. But also I multiplied the denominator by 3. Let's just check. 2/3 times a third is 2/9, and that's exactly what this fraction will be. Well, let's see if we multiply by 2/9 again, or 2/3 again, to get the next one. So we're at 2/9 here. If I multiply that by 2/3, I get 4/27, and if you look at this fraction, it is 4/27. So it does look like we're multiplying by 2/3 every single time. So our common ratio is 2/3, and again, as I've been saying all along, since common ratio is less than 1, this implies the summation can be written as A over 1 minus R, the infinite sum. So let's go ahead and rewrite this summation as an infinite sum. It is the summation n equals 1 to infinity of our geometric sequence, which we didn't write down, but we can now. A is 1/3 and R is 2/3, raised to the n minus 1. And because R is less than 1 in magnitude, this will be traded out for an A over 1 minus R. Multiply numerator and denominator by 3, and you'll get 1 over 3 minus 2, or 1. The question is, how much have we removed? 1. 1 full length. Now remember, this was just an interval from 0 to 1. We have removed the entire length. Everything from 0 to 1 we should have removed. We removed a length of 1. Yet, we will have an infinite number of points remaining because we keep all the edges. This is where calculus sings beautifully, is that you could remove a full length from an interval of length 1 and still leave an infinite amount of numbers there. That is mind-blowing. And this is why I love calculus so much. This is where you want to be. You want your brain to kind of be at the edge of infinity for thought. This is just beautiful stuff. Anyhow, I wanted to leave you with that because I think that's a great application. All right, I hope that this inspired you and got you excited for calculus, because this is calculus.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.